All right, so this is now 11:15, and it is Postgres versus the block size in Stream 1. So if folks want to go ahead and get going, whoever's leading this, please figure out who would be best to take notes, or at least get someone to take notes for this session, please. Thank you.
Right, so it was me who proposed this, so I guess it's up to me to give a quick introduction of or explanation why I think we should talk about this. I'm not sure. I do have a couple of slides.
So should we go ahead and start, or we give it 1 minute? But we probably shouldn't give it very much time because.
Right. So I do have a couple of slides, but I don't know how to present them.
I guess let's just start. Yeah.
I should be able to make you a presenter. Just give me a second.
I can take some notes on a piece of paper. Can I offer a few thoughts, or do you want to say something?
No, I'm not seeing it. Dan, are you able to make it so that Thomas can present, please?
I think like everyone.
Also, we're getting cross talk from a different session. I'm not sure what that is. Maybe that's just me.
The problem that we would like to discuss is.
I'm hearing it too.
Yeah, no, I'm hearing it still. All right, that might have been Dan again. But Dan,
I can volunteer to take.
Okay,
I can
Greg, yeah, if
volunteer
you
to
can take
take
notes,
notes if you want.
that would be great. Yeah, would appreciate that, Greg. Dan, is it possible to make it so that Thomas can present?
Thomas V.
Yes,
Yeah.
sir.
You have to do that because you're the host.
Okay, you're gonna have to help me then.
So go to the participants.
Yeah,
Go to
and I click on more.
Find him. And
Yeah.
on the right, you can see how you can make him a host.
Nope. I have chat, stop video, add pin, spotlight for everyone, allow to multi-pin. Oh, make host. Sorry, make host, not share video. Okay. All right, now I'm making you the host, Thomas. There you go. Now you can probably share. Sorry about that.
Cool. Okay, it's telling me I have to restart Zoom, so let me restart.
Okay, that's fine. So just for folks who are maybe just now joining, Thomas has got a couple of slides that he'd like to present, but apparently he has to like leave and rejoin Zoom, which boy, I hope that doesn't mean that we don't have any more hosts. I guess we'll find out.
I think it's just if you haven't given, like if you're on Mac OS and you haven't given access to the Zoom app to record the screen, like the first time ever that you do that, that's you have to restart the app.
Sure, but now I'm wondering, well, we'll find out in a minute if we have to do something weird. Hopefully he can, when he rejoins, he'll be the host still. We'll just give him a minute to rejoin when he gets a chance. Aha, he's back. He's not named Prague.
Yeah, I guess you need to make me host again.
That's gonna be tricky. Dan, can I make him? Oh, I can't make you a host again. Hang on.
Yeah, I handed that
No,
back to
sorry,
you.
I stole it back.
Oh, you stole back. Okay, good. Yeah, make
Who needs
Thomas
to be host?
Prague, Prague.
Choices, and we can, and especially where we can choose between the options.
Yeah, there you go. All right, Thomas, go ahead now.
Without considering cost.
There we go. Yay!
Look at that.
Good.
Cool.
Now, can Dan mute because of the, yeah, thanks.
Right. So one of the things that is important for a database is obviously block size. Once in a while, I do benchmarks to explore like how changing things would impact performance. And so I try to do this for the block size, both for the data files and for the wall. And I think it's actually interesting and becoming even more important because of the changes in the storage system. And also because we are like optimizing a lot of other stuff. So potentially smaller gains are becoming like more important. If you want to dig into the results, I have pushed them into my GitHub repositories. There are two repositories, one for PGBench, one for TPCH. I'm pretty sure during this talk, I will show some of the charts and results from that. Right. So why the block size actually matters and changing the right one, why I think it matters is that we kind of imagine this, right? We imagine that we have data files that are by default split into 8 kilobyte pages. And we have wall, which is also split into 8 kilobyte pages. And then we cache stuff from the data files into shared buffers, which obviously is using also 8 kilobyte chunks of memory, right, to match the data files. But what we actually do get and what we deal with is much more complicated, right? Because we have shared buffers using the 8 kilobyte pages, but then we are copying data into the kernel page cache, which is on Intel system, which is only like 4 kilobytes, right? The memory page is 4 kilobytes. We might be using huge pages or something, but that's like 2 megabytes or larger. So that's something we don't need to worry about here. And then the kernel is flushing that to disk, and the disks are like, there's a lot of variability in page size or like the addressable pieces, because the older spinning drives have been using like half a kilobyte, then that increased because of capacity reasons to 4 kilobytes. And the new systems like SSDs are using maybe 8 to 16 kilobyte pages. And there are even file systems or like network attached storage that might be using actually even larger pages to copy the data from the system, right? So there's a lot of flexibility, a lot of unexpected behavior, and also especially flash storage is using like a lot of different maintenance tasks, because for example, you can't actually overwrite existing data directly. You need to reset the pages first and so on, which if you have larger pages, for example, if you are writing data in large chunks and like, for example, 8 kilobytes, even if you modify just a couple bytes, the SSD has to essentially erase 8 kilobytes and start from scratch, right? It's even more complicated, but there is a significant cost of using larger pages, right? So there's a lot of things that does matter for the page size. And I think one thing I haven't mentioned so far is full page rounds, right? So if you have larger pages, that is potentially more efficient because there is less overhead. But we do need to, once in a while, write the whole page into wall, right? Which inflates the amount of wall and can even cause like reaching the checkpoint very quickly, which starts a new round of like writing full page writes, right? Which is really expensive. The other thing is that as you are increasing the page size, you make it more expensive to actually copy the data, right? So when we are reading the data into shared buffers, when we are copying the data into page cache and so on, that gets more expensive. We also need to, if you enable data checksums, you need to always calculate the checksum on the whole page, even if you modify just a couple bytes, which is also getting more expensive. It's a bit surprising, but it also affects cache hit ratio. I will show you a chart later. I mean, the larger the page, the lower the cache hit ratio for some reason. I already mentioned the OS page size, which is 4 kilobytes on Intel. I've already discussed like different page sizes at the storage level and the intricacies of new storage. And also, but that was mostly for like the data pages. But we also can modify the size of the block size on wall, which it might seem that using larger wall pages is clearly beneficial, but because of flushing the last page on commit, we actually can cause a lot of write amplification just because of this. So how much can we gain by tweaking the page size? So, So I will show you a couple charts from the benchmarks I did. Right. So there are some results from two machines. The interesting part here is the results, which are here. There are a couple runs for 16 megabyte wall segment. And for example, the most interesting thing we probably care about is throughput, right? So we have a throughput for 3 different scales. This is like a small scale which fits into shared buffers, and on the left is read only, and you can see that it's like there is very little variability, so it looks more like a noise, right? Green means better performance, red means lower performance. It's a simple color scale. In the read-write mode, it's actually a different story. You can see that increasing the wall block actually decreases performance, right? And actually the difference is like, I don't know, 10 to 20%. So 8 kilobytes give you like 87,000 TPS. And if you increase the wall block, it actually decreases performance. But changing the data block actually doesn't change much, right, to the performance. So that's the first observation. Then if we increase the scale to 1,000, which fits into RAM, but not into shared buffers, we actually see a pattern emerging, right? That actually benefiting from smaller page size. I'm pretty sure this is NVMe SSD with 4 kilobyte pages. So you can see a clear like 10% difference here just by going from 8 kilobytes to 4 kilobyte pages, right? And the read-only doesn't have this jump from 8 to 4 kilobytes, but there is some performance decrease once we start using larger pages, like 16 kilobytes or 32 kilobyte pages. That's like 20% decrease. And finally, the largest scale is even clearer, where by default in 8 kilobyte pages, we have like 42,000 transactions per second. And just by decreasing the block size to 4 kilobytes, you get like 50% performance improvement. Otherwise, all the parameters are the same, no difference, right? And again, we can see the similar pattern for wall pages, that increasing the size of the wall page actually hurts performance, right? The difference is, or the correlation is much weaker, but it still decreases the performance. And for the read-only, we see a similar story, right? For 8 kilobyte pages, you get like 250,000 transactions per second. And increasing switching from 8 kilobyte page to 4 kilobyte page, the performance actually jumps by like 50%, right? I don't have a clear explanation for that, but my assumption is that this is simply by aligning the page size with the internal SSD page, so that the SSD doesn't need to, for example, fetch two 4 kilobyte pages and combine them into the 8 kilobyte page, right? Which seems reasonable. I do have a lot of other charts like this, but I'm not going to bore you at this point. This is really, I think, the purpose of this talk is, or this unconference is to have a discussion about these things, right? So the question is, what should we do about making it easier to change the block size, right? So does anyone have like questions or ideas or whatever?
This is David. David Steele.
Yeah.
This is a little bit of a surprise to me because I thought you were going to go bigger, and it turned out that the best results were smaller, which makes perfect sense once you explain it. In a past life, I used larger block sizes in Oracle, but that was also with a OCFS file system that had been formatted to 32K blocks and all of these things that I'm sure they had optimized with Sun and et cetera, et cetera. The one thing that occurs to me immediately looking at this is that we have areas of the code where I mean, I think one of the reasons why we haven't made this a variable size is that there are certain pieces of the code that are optimized to have a constant in them. The checksum code in the page checksum code in particular is actually vectorized and unrolled using exactly the 8K block size. So, and there may be other places in the code that are actually, doing optimizations based on the fact that this is a constant. Any thoughts on that? Would we just compile some of the most common block sizes for that vectorized code?
Well, yeah, just to clarify, this is not using checksums at all. I haven't enabled data checksums here at all.
Right, I figured.
So this is just like regular build, nothing special. That reminds me, when you mentioned like larger block sizes, we often recommend using like larger block sizes for analytics, right? Or that's the common wisdom. But my experience with that is, and that in the other benchmark that I can show here. Which is like TPCH like thing. And the results from that are for data loads. I think that's perfectly true. Here, for example, that's a significant improvement for data loading, right? I mean, like instead of like 7,000 seconds, we get to like 5,000. Right. That's fine. But then when we get to queries,
the traditional answer in Oracle was that data warehousing applications benefited from large block sizes and OLTP applications benefited from small block sizes.
That's true, but this is like the total duration of the 22 queries in TPCH, and you can see some, like, initially it looks nice, right? We improve the duration quite significantly, but then it goes wrong, and for the larger block size, it actually misbehaves, right? I can actually show you probably, if I remember the query correctly, I think it was like 7. You know, like there is a lot of charts. I think it was 7. Right, so then you have queries like this, right? Where again, like the lower the duration it's green, the higher the duration is red, right? And you can see that we are like improving, then it gets worse, then it gets better, and so on. And I think query 9 might be even a better example. No. So there are probably even worse queries. And the simple problem is that the cost estimation and the query planning is obviously using the page size or random page cost and sequential page cost as input, but we kind of ignore the size of the page, I think, mostly, right? And if you have like, sorry?
I say, did you get a chance to look at the this regarding like using large page sizes to avoid toasting? Because that might be a significant benefit.
Yeah, I think maybe, but I think the TPCH isn't really using a lot of toasting at all, right?
I don't think it is, no.
Right. What I was going to explain is that we kind of use like number of pages, and if you use larger pages, it means like fewer pages. So which may change the cost estimate, and it probably changes the cost estimate like in different places for different operations. So exactly the thing where we recommend using larger pages it actually becoming problem because the analytics means complex queries usually, right? And that will start behaving in unpredictable ways. So I think there's a lot of work that needs to be put into like the costing in general. I think the benefits for the OLTP workload are much clearer and much smoother and easier to understand, right?
So there's another thing here related to what David was saying that are kind of related to the toasting indexes also. So like if we go down to 2K data blocks for B trees, then that reduces the max size of a key pretty significantly. And it makes me wonder if you almost have to, I almost wonder if you have to get to a point where you allow the indexes to be a different size block than the heap pages, which I realize is another big topic, but
yeah. I actually hinted on, you're essentially suggesting that we could have like different block size for different objects, right? So maybe indexes could use a different block size than tables, or maybe some tables could use smaller block sizes and so on. I think some databases do that, like if I'm not mistaken, Oracle allows that, but I can't even imagine like doing that in the code, right? Because then how do you actually cache the different size blocks in shared buffers? Like how would that work? I mean, like would the shared
Actually,
buffers...
I think that might not be the hard part. I think there, what Oracle does for like it just has a shared buffers area for 4K
size.
blocks and a separate shared buffer area for 32K blocks, and
Exactly.
they get cached in the separate caches. But I worry about there's probably other areas like full page writes and who knows, like there's other areas that are going to, sorry, I'm pouring some water, that probably would get very confusing. Like if you have two full page writes in the same wall and one of them is 4K and one of them is 32K, like
Well, yeah, I can definitely understand that there is a lot of complexity that might be, causing this, right? I mean, like my idea initially was that we would at least allow changing the block size at the initdb time, because at the moment, if you want to change like the block size, you use a different block size, and you know that you want that, you have to build your own packages, which, I mean, is possible, but it's not great, right?
Yeah. Regarding that, running it only at initdb, did you actually validate the performance of that? Because a lot of code is compiled on block size.
Sorry, what?
A lot of our code is dependent on block size being a constant and compiling those constants away and so on.
Well, yeah, I understand that, and that was kind of the problem with the wall segment size too, right? I mean, like initially it was defined when building, and it was a constant, and then we made it actually into something that is specified at initdb. So it's no longer a constant, or it's no longer a macro or anything. And I would imagine that for the block size, it would be similar. Obviously, if we want to allow like multiple block sizes at the same time, like for different object types or whatever, it wouldn't be even this simple, right? It would need to be even more elaborate, because you would need to request the block size for individual objects, or I don't know, maybe table spaces or whatever.
I think it's more complex than just not being a constant anymore, or macro anymore. Like the max tuples per page is calculated from the block size. The thresholds for toasting are calculated from the block size. The max index tuple size is calculated. Like some of these things, the logic of the code assumes that these things don't change, not just
Yes.
that they're written assuming that it's a macro, but like even if they used a variable, they wouldn't work correctly.
Agreed. I think it's more akin to changing, like for instance, if we change the data segment size from 1 gig to 2 gig, that's a lot closer to what we did with the wall segment size. I think changing the block size is, I think, an entirely different beast, and it took a couple of years to get the, even the wall size, quite right. The first patch didn't go because it just had too many niggling little problems in it. So I'm not saying it's not worth doing. I'm saying I don't think it's analogous changing a wall segment size. I think it's going to be a lot harder than that with a lot more unintended side effects.
I understand. I mean, yes, there's definitely going to be a lot of fallout from that. My view on this is that I'm not sure if we actually want to do this or if it's worth it, right? I'm just saying that if you have a large transactional workload with a lot of writes or even just reads, you can gain like 50% from using a smaller block size or whatever your storage is using, right? Which seems quite a lot, right? I mean, compared to other optimizations that we do, which bring maybe 5% in some cases and so on, that's quite significant, right? But of course, I'm not sure if it's worth the effort, right? I don't know.
I think one thing I remember from the wall segment size patch was one of the reasons why it had to through the first time was that it caused problems even when you still picked the 16 meg wall segment. Like we weren't confident that all the changes we made to all the macros and all those sorts of things were actually correct, and that it didn't seem to be adequately tested. In this case, I mean, I think that the idea is if you could at least prove that it was adequately tested to start with, make the default size 8K, then it's sort of a your mileage may vary kind of deal if you change that default, as far as how it's going to affect the planner, how it might affect checksum calculation, how it might affect, all those sorts of things. So that's one thing to keep in mind is that we don't have to make it perfect have perfect optimization for 16 or 4K pages if there's no regression on the 8K page, right?
But shouldn't we know why the page size makes a difference? Like if, in case there's a way we can get the benefit without requiring page size changes?
Well, there are a couple of things. I mean, there are things that Thomas brought up. One of the things that was a big deal for us in my Oracle days was just the number of pages you had to deal with in these, at the time considered extremely massive, like gigabyte scale page caches, 64 gig of page cache and things like that. Just reducing the number of pages you had to deal with and scan and when you did truncates and stuff like that by 4 actually ended up making a huge difference. So it was also could be, just the management of the buffer cache could be an argument to go to 32K pages, especially in our case where we had a really write heavy workload, but most of the data was never actually looked at.
Right, but this is the opposite case. We're making it smaller, having more pages, getting it faster. I think we have to find out exactly why is it different? If we see, maybe is it the transfer from Postgres to the kernel cache? Is it the kernel cache to the storage? Is it something else? Like I definitely wouldn't go in this direction until I was sure where the benefit was coming from. And you have to do like a flame graph or something.
Yeah, I mean, I definitely get that. It's just clearly we're down here.
We could brainstorm a bit about possible mechanisms. I mean, David still suggested one, but I can toss out a couple others. Like I think the reason traditionally why data warehousing applications used large block sizes was that you just got higher data density in the blocks. You fit more tuples and had less block header overhead, you also got more sequential I/O because you were reading and writing in larger chunks and not depending on the prefetching as much.
Right.
And the flip side of that is actually what Thomas mentioned, that in OLTP applications, if you have larger block sizes, you are sometimes forcing the I/O system to read in data in order to make changes to just part of that. Like, if you're dirtying 8K out of a 32K SSD page, and in order to write that, the RAID array or the SSD needs to read in the whole 32K in order to dirty just part of it. That's
Yeah,
I don't know what to call that.
Yeah, I think the internals of the storage, especially for SSDs, are a big part of the gains here, right? Because Postgres is always overwriting the whole page, right? I mean, like we never do partial writes to the operating system and to the storage, which means we always dirty all the pages maintained by the SSD, which puts pressure on on the cleanup that is done by the SSD on resetting the data, the blocks, so that it can be written again. So I think that's a huge part. The other thing is, and I haven't actually expected to see this originally, is actually that this affects cache hit ratio, right? I have actually shown on one of the results, which is cache hit ratio for the PG bench, and you can see that even on the read-only case, there is quite significant difference in cache hit ratio depending on the data block size, right? I mean, like it's like 75% versus less than 60, which is quite significant. And this is quite counterintuitive, because the smaller pages should actually have more overhead, right? Because the page header is still the same size and so on. So there should actually be more the 1 kilobyte pages, and we should have a lower probability of hitting the page that is already in memory. But it's actually exactly the opposite. So I don't have a very good explanation for this, but it actually seems quite regular in the results.
So, sorry, go ahead.
Yeah, no, I don't have anything.
So another thing I thought of that maybe doesn't explain the cache hit ratio necessarily, but I could imagine writes being more performant on smaller, or OLTP writes being faster on smaller page sizes with respect to pseudo-random indexes, because you would be like, if the number of writes to an index that happen per full page write is small, right? If you're flushing a wall, if you're doing checkpoints every 5 minutes, and your index is very large, and you're pseudo random spraying updates across it, then effectively you're approaching like one tuple changed in like per page that gets FPI'd, right? But that would mean that with smaller pages, the amount of wall write overhead for each of those full page writes, it would be significantly smaller.
So I'm not sure if I actually know what you are talking, if this is actually what you are talking about, but this is essentially the amount of wall written per transaction, right? And this data set is like much larger than a checkpoint. So you can see that with 1 kilobyte page, we actually write just over 1 kilobyte into wall. But with 32 kilobytes, kilobyte pages, we write almost 24 kilobytes per transaction, which is exactly the write amplification for because of full page wrap. Right.
That's interesting. It's interesting for two reasons. One, I mean, it makes me start wondering whether we need to do full page writes of whole blocks. Like, we know the reason for full page writes is to protect against torn hardware blocks. But I wonder if we can separate that from our shared buffers blocks. But
No.
it's also interesting that the number goes from being larger than the block size to being smaller than the block size.
So
I'm a bit confused though.
So
How
I
large
think,
are the block sizes? Because
so
we don't.
we do full page writes to protect the not the hardware block size, but to protect the Postgres block, right? So actually, we do expect this to be a bit larger than the Postgres Postgres page. But
like, hypothetically, like, if we had very large shared memory buffers, and then instead of keeping a dirty bit, we kept a bit mask of which parts of the page had actually been dirtied, there would be no need to do full page writes on the parts that hadn't been dirtied.
So I'm not sure about that. I think the full page writes are quite complex, but
fair enough.
I'm pretty sure that's what happens here is that we do, for example, touch the same page multiple times, and that brings the average down, right, and things like that.
Yeah.
Or I'm not sure if we do compression or whatever on that. That's also possible, of course, right?
The data block sizes in those charts,
right?
The first two columns, are they 1 and 2K data blocks?
Yes.
I thought we didn't support less than 4K.
We do support up to 1 kilobyte, yeah.
Huh. Okay.
I mean, yeah, we do. I haven't tried actually using a file system with smaller block sizes, right? Because even on Linux, for example, you can create a file system with like 1 or 2 kilobytes, kilobyte pages. It's 4 kilobyte by default, but you can use smaller.
How does, I mean, this is getting off topic, but I wonder how Linux, like, the memory pages are 4K. I wonder how that would even work.
I want to point out that we've got about 15 minutes left. So, Thomas, if you had anything in particular that you wanted to, ask about that hasn't been addressed or anything, I would, might be a good time to think about that. I did want to just also share a random thought, because that's what I like to do. Have you thought at all about, is there a way we could do JIT for dealing with these differences, just-in-time compilation of bits of code? And I think the other question I'm wondering about is how we're going to do, what we're going to do with shared buffers. It seems like we would need to split that up into different components, which I've kind of always thought might make sense to have separated shared buffers, maybe like on a table space basis, back to, and that could then correlate to block size. I don't know. Just some different random thoughts about that. But I just wanted to share those two thoughts real quick in terms of this particular discussion. But yeah.
So I have absolutely no idea about JIT. How would that work? Or I mean, like my initial assumption was that we would at least allow like easier way to use and use different block size in an easier way without having to rebuild the binaries, right? So I'm not sure. I don't think the main cost here would be the CPU time or anything, and for having different parts of shared buffers used for like different pages, different block sizes. I guess that's the easiest way to support like multiple block sizes, right? Probably. But I kind of dislike the fact that you need to essentially do that in advance, right? I mean, like you need to specify in advance not only how large the shared buffer should be, but also that half of that should be for 4 kilobyte pages and half of that for 8 kilobyte pages or something like that. And I think that's extremely difficult to do for users, right? Like it's essentially yet another parameter that needs to be tuned by the user. And so, I mean, it's probably the easiest way to do that, and I don't have a better idea how to decide how much should be used for what block size. But I kind of dislike this expectation that the users will tune that and will pick the right size. I don't believe that.
Okay. Well, anyhow, yeah. So if you had anything else, like I said, about 10, 15 minutes left before this session ends for any kind of final comments, questions. Otherwise, happy to let the conversation continue. I just want
I'll post the link to the notes again if anyone wants, in particular, if Thomas wants to put a link to his presentation in the notes, that would be good. If anyone sees anything I missed or want to correct.
So I will.
You need to send that to
the share links to the GitHub repositories. And
am I sending it to Stephen? Oh, I'm sorry.
And I actually will have a talk about block sizes at the EDB conference at the Postgres region. So that hopefully will be like more coherent and more consistent than the random discussion here.
Yeah, I mean, I guess the purpose of the notes is if someone wants to work on this, in particular, if you want to work on this, to remember the ideas or comments people tossed in. So if someone did toss out an idea that they think is important and I missed it or didn't characterize it accurately, feel free to correct them with the notes so that Thomas has, or whoever else wants to work on it, has your ideas accurately represented.
Yeah,
I only put names a couple times on. I wasn't trying to. Yeah, I wasn't very consistent. Sorry.
No, I think that's fine. I mean, like I'm essentially looking for two kinds of feedback. I mean, like if anyone wants to do some of the coding and like explore how difficult would it be to do some of this, fine. But I was looking for like two kinds of feedback. One is like interesting questions, or like this looks strange. It should be behaving like in different ways, and we should explore this. And the other thing is like ideas. What might be the reason for for the improvements, right? I have mentioned some of my ideas. What I suspect is playing the main role here. but maybe there are some other costs that I'm entirely ignoring. So that was.
I think Bruce's question is a good one, that if we're putting in lots of effort to support different block sizes, we should really understand the mechanism that those different block sizes are how they're having the effects they're having. The other thing, I think there was a lot of interest in supporting multiple block sizes, and I don't think that was your plan. I think it doesn't have to be your plan, but it's worth knowing when you implement something at initdb time, not to sort of paint yourself in the corner, because it's pretty clear that down the road someone will want to make it more dynamic.
Yeah, sure.
So you can, instead of like trying to calculate lots of things at startup, like you can calculate them on demand, so that later when it's more dynamic, that they don't have to undo your work.
Yeah, but I think that Thomas has already shown that fighting the kernel layer cache is not a good idea. And I don't think that we can come to a closer conclusion before we get direct IO in and can eliminate that layer in order to see what benefits the different block sizes are. So I think a good idea would be just to have it as a static startup parameter for initdb.
What I'm saying is, I think as a development plan, having it be at initdb is a fine first step, but don't write it assuming that like it will always be at that. Like, for example, don't pre-calculate lots of other constants. Don't put in lots of effort to pre-calculate lots of other constants when it would be more convenient to calculate them as needed, because down the road they're probably going to need to be calculated as needed anyways. I'm sort of saying, like, it's fine to have an intermediate goal and a stepping stone towards like we can't do multiple shared buffers now because of the issues you pointed out, but when someone does tackle those, it would be good if the code wasn't actively working against them. I think the point about direct IO is good too, though. So I guess we're out of time. Stephen? Someone?
We have kind of formally about 5 more minutes, and then we're into lunch. So folks are certainly welcome to continue to use this stream to continue chatting about this topic, or really whatever topic people want to. But we'll kind of have a formal break for lunch, so people can step away and go grab something to eat and whatnot. And then we'll start back at 13. I think it was 13:15, whatever the schedule says. Yeah, 13:15, and that'll be state of the SQL standard for the next thing. But yeah, we do have another 5 minutes or so here if people want to continue talking.
Do you mind if I ask a couple of noob questions here about this? Has anyone given any thought to doing something a little bit more radical along the lines of what Oriole DB is, and replacing the entire buffer caching layer with something else that's a little more closely aligned to the hardware? And that's number one. And number two, and I'm sure that this has been considered and rejected many times in the past, but memory mapping. Just kind of dropping all this on the operating system and letting it figure out what to do.
I have thought a lot about memory mapping, but I had a crazy plan to implement our existing buffer cache, but never doing I/O, just memory mapping 8K memory maps. That wouldn't have worked very well, but it might have been interesting.
Well, the issue there ends up being that we have to be able to have control over when things get written out, right? That's the problem, right? That's why you can't just do memory mapping.
There is mlock, but it's not. It doesn't quite give you all the control you need, and the kernel is not prepared for thousands of mlock ranges, or maybe it is, but not millions of mlock ranges.
It gets a little more complicated. I think Heike did a test, and he found he got a little bit of benefit by eliminating the buffer cache, but the system became very sensitive to the sizing of the shared buffer cache. So if you could size it perfectly, you got a little benefit, but if you were off, you got a big performance hit. So it was a kind of case where removing the kernel cache made it like overall a negative, even though if you were really good, you could make it a small positive.
Are you talking about direct IO or memory mapping?
Just eliminating the kernel.
Right.
That would be direct IO. Yeah, I mean
I think it's sort of similar. It's sort of the same idea, but the two sides of the same coin. Doing direct IO means one way or the other, you're avoiding double buffering.
Right. You're avoiding. Yeah.
So memory mapping means doing it all in the kernel, but you're kind of taking control over what the kernel's buffering in some ways. So it's kind of looks similar at some level. I think, my crazy idea of doing 8K memory maps is probably crazy. The way you would do it in a greenfield would be memory mapping the whole table or 1 gig segments. But I didn't see a way to marry that with the. In a 64-bit world, once you have 64-bit address space, you could just say, okay, we're just going to memory map the whole database. But yeah, there's the problem about controlling when pages get written out, and then there's the problem of and I think there was some discussion in the kernel about getting control over that.
I think there's a call. Isn't there an OS call you could say that, commit write hard to disk this range of the memory map?
Yeah, but the problem is we want to do the opposite.
Yeah, it's the opposite. We have to be able to tell it, you cannot write this yet.
So what we have to be able to do is say, so if we're letting the kernel decide when to flush things out,
right,
we have to be able to say, if you need to flush things out, you need to check that these other things have been written first, and somehow ensure that they're written before it flushes things out, either because we prevent it from flushing things out, or there's some sort of callback of some sort or something. And it's a generic enough problem, it's a common enough problem that I think the idea was the kernel would provide some sort of interface where there's some sort of flag or counter or something, and when you're f-syncing transaction logs, you're telling it to flip the flag, and that allows it or increment the counter or something, and it would kind of mirror the way we use I don't know that it ever got to be a very concrete proposal, but it was kind of like somehow we have to push the logic that we do with LSN into the kernel page flushing mechanism, which is not.
I think essentially for a long time handing over stuff to kernel and letting kernel to do the stuff worked quite fine for us because it also is like more portable than the memory mapping implementations.
Yeah.
That was fine. But I think the memory mapping is, there is much more difference in behavior on different platforms. So we would maybe support it on some selected platforms, but also I think we are at this stage when we actually need to abandon this generic approach, and we need to take responsibility for figuring out which stuff to write, in which order, and so on. And that's essentially what a lot of the work recently has been about, right? I mean, like the direct IO is about that. The flushing of shared buffers is about that. Both of them have been done by Andres, right? I mean, like, and those are things that we can't actually conceivably hand over to kernel, because kernel has absolutely no idea about which stuff needs to be written immediately because it directly impacts the front end work, and what can be written in the background asynchronously, for example, right? And things like that. So I think the memory mapping has a lot of issues. First, because of the API, which is fairly limited. And even if we get some improvements in Linux, we will not have that on other platforms. But also because if we get sufficiently rich implementation or API, we will essentially be able to do that without the memory mapping, right? So I don't think the memory mapping is a way forward. Maybe for some special storage systems, for example, the NVMe SSDs, or sorry, NVRAM.
The
It is
persistent
based on
transactional storage things. Yeah.
That's essentially based on it requires actually memory mapping stuff, right? Because then it actually gets directly to the persistent storage.
So that suggests something else. If different implementations will work better in different environments, maybe we should abstract away the storage layer completely. And I think there is some of that, but I personally found it very difficult to implement my own storage under the hood for a special need. It just wasn't easy to, I think there's the old magnetic disk, md.c and stuff. And I just,
I think there is definitely a lot of assumptions about how the storage behaves, which is kind of encoded into the magnetic disk interface and so on. But also there is a lot of like optimizations that are tailored for different storage systems and are kind of hard coded into the current implementation, right?
So I just want to make sure that we get an opportunity here to kind of formally close out this portion of the unconference talk. I'm fine. You know, obviously people are welcome to continue having this dialogue in this stream, but I just want to kind of make a point that you know, we've hit the time limit on this particular talk, and so you know, folks are free to take a break and go and you know, take care of anything they need to do and maybe have some lunch and whatnot. You know, for those who want to continue to stay, feel free. I'm going to step away myself for a bit. Obviously, this is all, you know, interesting conversation. As a reminder, we're going to restart at 13:15 U.S. Eastern / Ottawa time, and that's when we'll start with the next session in this particular stream, which is going to be the state of the SQL standard that I believe Peter Eisentraut was going to host.